Welcome to the lesson on the derivative of sine x. So right now we don't have a rule for sine x, so my hope is that most of you, given that we don't have a rule, so your first instinct would be to try the definition of the derivative. So that's first principle is using the limit definition, which is f at limit as h goes to 0 of f at x plus h minus f at x all over h. So in this case f at x is going to be sine x. So we'll put that into this function, sine of x plus h minus sine x all divided by h. So now you might look at that and say, okay, well, direct substitution is not going to work. I'd end up with 0 over 0. So we obviously have to simplify this in some way. So the question is, how are we going to do that? So looking at this, sine of x plus h, those of you who remember your trig identities might recall this identity. Sine of a plus b is equal to the sine of a, the cos of b plus sine b cos a. So if you don't remember that, maybe wouldn't be the worst idea to go back and look at your trig identities. So we're going to use that in this function. So it's going to be sine of that first, x, times cos h plus sine of that second, which is h, cos x minus, and then we have the minus sine x there. And that's all over h. Okay. So what are we going to do with this? Well, you might notice there's a sine x and a sine x there, so first instinct might be to try grouping those. Actually, we'll just factor them. Okay, so I'm going to group this, and then I'm going to factor out the sine x. So I'd have cos h minus 1. You know what? I'm going to skip a couple steps. So I'm going to split this up. So that's this part, and then I still have this sine h, cos h in the middle here. So I'm going to split that up and write it as a separate limit. So to save space. So we have sine of it h cos x all over h. Move down a bit. Oops, so we're running out of room. Okay, so looking at this, what you might notice is that this sine x here is constant relative to what we're taking the limit of, which is h. So by our constant multiple rule of limits, we can take that out in front of the limit. So inside the limit we'll have cos h minus 1 over h plus, and then again I have a cos x, which is constant relative to h, so I can take out the cos x, and then inside that limit I'll still have sine h over h all over h. Okay, so looking at these limits, I've simplified it to limit as h goes to 0 of cos h minus 1 over h. Now that's a bit tricky of a limit to deal with, as is this one, sin h over h. And really, you can actually figure out what those are equal to using sort of more advanced calculus methods. If we wanted to figure it out right now, my suggestion would be to just use a table, take smaller and smaller values of h, just to kind of see what it's approaching. It wouldn't prove what it approaches, but it would give us an idea. So I'm just going to actually kind of tell you what it is. So this limit as h goes to 0 of cos h minus 1 over h, this is actually equal to 0. And this limit over here, sin h over h, limit as h goes to 0, is actually equal to 1. Not obvious, so that's not obvious. Just looking at it, you would not see that. But if you do the table, you would notice that that's the number that limit's approaching. So right here we end up with sin x times 0 plus cos x times 1, which works out to just cos x. So that's the derivative. So the derivative of sine turns out to be just cos x. Okay, so what we just showed was that if f at x is equal to sin x, then f prime at x is equal to cos x. So we kind of glanced over sort of the derivation or proof. There was a few holes with those limits in there. So it's a sort of good easy thing to remember. Sin x, derivatives cos x. So a much more intuitive way of actually developing this rule is to do it by graphing. So I'm not sure how great my graph's going to be on this thing, but I'll do my best. So we know that sin x looks something like that over a period, so that's rid of 2 pi, and then sort of the other period looks something like that. Amplitude's 1, comes out to negative 1, this would be negative 2 pi. So this here is the graph of y equals sin x. Now what we're going to do is graph the derivative of this. So we want this to be dy by dx. So if you remember how to graph the derivative, what you're going to do first is sort of look at where the tangent is horizontal. It would be these, over these 2 periods, be these 4 points. So what point is that? Coming down to the derivative. What point is that? Well, okay, sorry. We know that at these points with horizontal tangents, the derivative is equal to 0 because the derivative is just the slope of the tangent, and the slope of the tangent at those points is 0. So what are these points? This point would be pi by 2. This point would be 3 pi by 2. This point would be negative pi by 2. This point would be negative 3 pi by 2. Grab another color. Oh, that's a good one. Alright, so we have this point, this point, this point, and this point. So we know that the derivative goes through these points. That's the x-intercepts of our derivative. Now the question is sort of what's happening in between them. So let's look in between here and here, between negative pi by 2 and pi by 2. Well, the slopes of the derivative are positive, so the derivative is going to be above the x-axis, where is it at its highest value? Actually looks like it's at its highest value right about there. The question is, what is the slope right at that point? Just kind of to estimate it, we'll say it's about there. Turns out it's exactly 1. So the derivative's got to look something like that, and it turns out that this height is 1. And what does it look like in between here and here? Well, the slope of the tangents are negative. And again, so when is it the most negative? Turns out it's right there at pi. So comes down, looks something like that, and then again in between here and here, you've got negative slopes. So something like that, and then here to here, you have positive slopes. I'm going to finish it on the right side too. Again, positive slopes. So looking at this, that should look familiar. What does that look like? That looks like y equal, cos x. So y equals sine x, dy by dx equals cos x. So that's the way I like to sort of remember that rule, using the graph rather than that derivation.